Hello there, everybody. My name's Phil Lamar, and I'd like to welcome you to NASA's Ask the Astronomers Live, the show where we have live astronomers online live here to answer your questions about the universe. We do the live part, you do the ask part. And you can ask your questions of our scientists in the comments section at the Universe Unplugged website. It's also where you can find out about upcoming shows and see lots of fun astronomy videos. And that's, as you can see on the bottom of the screen there, universeunplugged.org. And when you do submit your questions, make sure to include your social media handle, which hopefully is even your name, along with your question so that we know who we're answering our question to. All right, today we are talking to two astronomers who study 7 planets that orbit one of our nearby stars. So that's 2 astronomers, 7 planets, 1 nearby star. And the first of our 2 astronomers is Dr. Eric Agel from the University of Washington. Hey, Eric.
Hello.
Eric, you'll start by telling us a little bit about yourself and the work you do.
Well, thanks for having us on the show. I'm an astrophysicist and professor of astronomy at the University of Washington. I spent my career studying black holes, gravitational lenses, and planets. And in the last decade, my work is focused on transiting exoplanets like the ones we'll talk about today. I build models to detect these, measure their properties. I've discovered some new planets with the Kepler spacecraft, and also use the Spitzer Space Telescope to create a map of an exoplanet.
Wow, who knew that? I figured all the hard work was just finding them, but you apparently do all the work after they're found.
Exactly, yeah.
Fortunately, you have some help, and fortunately, on the show today, we have some help. We have Dr. Victoria Meadows, also at the University of Washington. Hi, Vicki.
Hello.
Hi. Tell the audience why we're so impressed with you.
Okay, well, I'm a professor of astronomy and I'm director of the astrobiology program at the University of Washington. So we're training scientists to search for life in the universe. I study terrestrial planets, so that's rocky planets like the Earth and Venus within our own solar system. And I'm very interested in studying the smaller, possibly rocky planets that we're going to find around other stars. And I work looking at trying to understand what the planet's atmospheres in particular are like, and to figure out what they're made of. So what the planet is like.
Now you mentioned you're looking at rocky planets, because I'm presuming those are the ones that are most likely or probable to have some form of life. So is that one of the reasons?
That's a great going-in assumption. I mean, at the moment, where we're looking for life that we could at least recognize, and so where we think that, you know, if a planet has an ocean on its surface, then it's more likely to be able to support life, and that means it needs to have a surface, so it needs to be rocky. So that's why we're very interested in rocky planets.
Got it. I love that. Now, and audience, how many of us knew the term astrobiology? Vicki did. All right. So today we are going to be talking about this amazing group of 7 planets that were discovered around the nearby star Trappist-1. Now, Eric, Vicki, can you guys tell us a little bit about their discovery and maybe even why someone named a star Trappist-1? Eric?
Yeah, the story goes back, 30 years to the first discovery of planets orbiting other stars, which we call exoplanets. Exo because they're outside the solar system. And after the first ones were found, they had very different properties to the planets in our solar system. We found very large gaseous planets orbiting very close to their stars. It was tough going to try to find rocky planets more similar to our Earth. And so about a decade ago, 2010 or so, there was a Belgian astronomer, Michael Guillon, who developed a robotic telescope to monitor very small nearby stars. He reasoned that if he could look at the smallest stars, he could find smaller planets. He carried out a survey. He dubbed it Trappist, and that's a backronym. I mean, it's in honor of Belgian beers made by Trappist monks. And he located this robotic telescope high in the mountains in Chile to get a better view of the southern sky. And so by 2015, they had surveyed 50 stars looking for transiting planets. A transit is when a planet passes in front of a star. And this is fairly improbable because most planets are going to orbit randomly on the sky, and it's only occasionally that their orbits will pass edge-on, meaning the planet will go in front of the star. And so we had to look at a lot of stars to have the chance of detecting planets. And so by 2016, they had found their first star that they'd surveyed with the planet system of 3 planets. And so that was called Trappist1 because of that first discovery.
I see. And of course, the reason you need it to be a planet that passes between where we're looking and the star is because if it's going around the star that way, we just won't be able to see it, correct?
Exactly, yeah. So you have to get lucky, and therefore you have to look at a lot of the stars. Occasionally, especially since planetary systems are fairly flat, you'll get a lucky case where several planets will go in front of the star, and you'll be able to measure their orbital periods and see the shadows as they pass in front of the star. That's how we detect them. We see the star get a little bit dimmer for a percent or so for about a half an hour or a little bit more. And that's how we detect these planets.
Well, then see, now you've told me what our main goal in creating spacecraft should be. So we can see better.
Exactly.
So we can get different angles. But the fact is, we've been able to find some exoplanets, and particularly these ones about Trappist-1. Now, Vicki, can you tell the folks what makes these planets so special?
Yeah, sure. And actually, if we could have image 5, that would be great. So the really important thing is, first of all, there are just so many of them. So if you look at this image here, you can see the Trappist-1 system, and there's actually 7 planets. They're all roughly Earth-sized, and if you look down at the solar system, you can see that the only roughly Earth-sized planets in our solar system are Venus and Earth. But in the Trappist-1 system, we've got 7 of these guys potentially to study. So we're very excited to see what other planets the same size as the Earth might look like. Also, 3 of them are potentially at the right distance from their parent star to support liquid water on their surface. As I said, that's what we think makes a planet more likely to be habitable, able to support life. So there's this concept of the habitable zone, which is, that region around a star where if you place a planet with, roughly Earth-like atmosphere, you would expect it to be able to have an ocean on its surface. So in our solar system, we have Earth and Mars within that habitable zone, but in the Trappist-1 system, we've got 3 planets, E, F, and G, that are all within that habitable zone. So that's super exciting to be able to have planets that are roughly Earth-sized and at the right distance to potentially support liquid water and potentially life.
That's so funny. It just makes me feel like, looking at how many planets are in the habitable zone around Trappist-1 versus our solar system, it's sort of like being from Iowa and going to New York for the first time. There's so many here.
Yeah, there's a lot, and it gives us a much better statistical chance of finding something really interesting.
Interesting. Now, we titled this episode, our subtitle was weighing an exoplanet. Now, how do you weigh, and why do you weigh an exoplanet? Who wants to take that?
That's a great question. Yeah. So we do this with lots of telescope time. If you want to show image 6, we used quite a few different telescopes to study this planet system. So at first, with the ground-based discovery I mentioned in Chile, we then followed these planets, followed the star with other telescopes on Earth, and we started to find indications of additional planets, and eventually it got very confusing. And so then we just applied to the Spitzer Space Telescope, which is the upper left telescope here, to observe the star for 20 days straight. And that's when we sorted everything out and found, wow, there's 7 planets orbiting the star. We see shadows of every single one of these planets. The closest one orbits in a day and a half out to the outer one that takes about 19 days to orbit the star. And so with that 20-day discovery, we knew the locations of these planets. We knew when they would be going in front of the star. And so over the next several years, we continued to use the Spitzer Space Telescope, the Kepler telescope in the lower left, called K2 and its successor mission, as well as several ground-based telescopes. The Speculos telescope is depicted at the bottom, which is the successor to the TRAPPIST survey. And then the lower right is Hubble, which also looked at the star. So we had all these and more telescopes trained on the star for several years, waiting until each of these transits occurred and timing when that transit occurred. So with those measurements over several years, we were able to look at the planet's interactions. And so if you roll the animation, this shows a simulation of the system as you would see it if you're looking down at it. So about 90 degrees from where we actually see it, where we see the planets going in front of the star. The size of the star and the planets are exaggerated. And here you can see animation of just what would be the two innermost planets in this system. Every time they pass each other, the gravitational pull of the two planets causes them to get a little bit closer, and then they separate. And so that causes the planet's orbits to change slightly. It's like a ticking clock, but it's not ticking precisely. And so every orbit, when the planet goes in front of the star, we measure the time at which it goes in front of that star. And if the planet's just interacted with that planet, then we might see it come a little bit earlier or a little bit later. And it takes some time for these interactions to grow with time. It takes, they kind of do this dance that happens every 500 days or so, kind of like the diagram I've drawn on the chalkboard behind me. They pirouette around the star, and they do it in a synchronized manner, at least the outer 5 planets do. So it took about 2 pirouettes, about 1,000 days for several years to get enough data to be able to measure these gravitational interactions between the planets. And from that, we were able to get very precise measurements of the planet's masses relative to the star. We actually measure their mass, not their weight. Weight is defined on Earth, but mass is something has in outer space. Mm-hmm. With those measurements, we were able to then use these data to try to understand something more about the interiors of these planets.
I see. Oh, that's fascinating. So the weight, rather the mass of the planet, determines how much gravitational pull it has. Exactly. And you can measure its effect on the other planets. By seeing how much it affects another planet, you can figure out over time what their weights are in relation, well, what their individual weights are by looking at how they react to each other.
Exactly, yeah.
That's okay. That's why you weigh them and how you weigh them. Okay. Although I do have to say, I want to ask Eric, you said you had the, was it Spitzer for 20 days straight?
Yes.
How many other astronomers were calling you angrily? It's like, checking out the book that everybody needs for the exam. It's like, you can't keep it the whole time, Eric.
Fortunately, we had a big team. So there were about 30 astronomers from 3 continents, at least, that were working on this. And so we had a big enough group that we couldn't get pushed around too much. But there's actually a time allocation committee that gave us the time. So we were fortunate enough that they were willing to grant that, because at that point, we didn't know there were 7 planets. We just had some suspicion because things from the ground didn't make sense. We couldn't really disentangle what was going on.
Interesting. And Vicky, the amount of data they were able to get from that, what does this information tell us from your perspective about what the planets might be or look like, or
Yeah, no, that data set is amazing, because the incredibly precise measurements that Eric and his team got means that we're actually able to start to figure out what the planets might be like in their interiors. So, because Eric and the team were able to measure the masses so precisely, and we had the sizes because they transit, it meant we could figure out the densities of the bodies. How dense are they? Are they fluffy things like gas, or are they dense things like rock? And so if we look at image number 3 here, what we were able to do, the amazing precision on the measurements meant that we're now able to start to think about, okay, what are these things like on the inside? And so the team came up with 3 hypotheses for what it would be like, and they're really super interesting. So one of them, so the bottom line is the densities that were measured were all sort of uniformly little bit less dense than the Earth, right? So they're probably terrestrial planets, but they're a little bit fluffier. And then the question is, why is that, right? So the three theories we have are, well, maybe they look just like the Earth for the most part, but their iron cores are smaller. So that would make them less dense overall if they had less of an iron core, like, half or 2/3 of the iron core that our own planet has. Or they have no core at all, which would be fascinating, which would be that, they have all the ingredients to make a terrestrial planet, but there was so much water in there and it reacted with the iron. So you ended up with basically rust through the planet that was coupled into the silicate in the mantle. So it's all mantle, no core. And I think the most fascinating theory is that they pretty much look like the Earth, but they have loads more water in their either in their interiors, or in this case, we modeled the oceans on the surface of the planet. So they could be sort of more like water worlds. And that might make them less dense overall, just having way more water on the surface, or either as a steam atmosphere for the hotter planets. So with those precise measurements, we can start to actually try and figure out what these things are like.
I see. That's right. That's one of the three things I remember from high school science: volume times mass equals density. And so, and from those calculations, you can come up with those amazing theories. Wow. Can't wait to figure out which one is right. But Eric, Vicky was talking about how precise the measurements were. How was your team able to achieve this level of precision?
Well, it took quite a bit of time. So the 7 planets were announced in 2017, and because of the interactions between the planets are fairly small, as they interact over time, their tugs on one another can add coherently and grow in amplitude. And so you get these sort of oscillations in the times at which the planets pass in front of the star that have a period of about 500 days. And so the other thing is that we actually have limited times when we can point these telescopes at this star. It's only certain times of the year where we can actually take a telescope and point it at the Trappist-1 star. If we're using a space telescope, the limitation is that you don't want to point that telescope too close to the sun, and you don't want its solar panels to not point at the sun. If we're on Earth, then we have to wait for darkness, and that only happens in certain times of the year. Mm-hmm. And so it took literally about 4 years worth of monitoring these planets to really precisely pin down the orbits of the planets around the star and the interactions between the planets. We also had to do quite a bit of analysis. So this was all, this analysis was carried out on a grid of computers over 9 days. I think we had 30 computers turning away. So it was quite a bit of computational effort that took about half a year, and then it took about half a year to get published. And it was published about a month ago. So it was quite a long and arduous process to get to this point. But if we can show image number 8, this is actually the final result of our data set. The plot shows the radius of each planet versus its mass, and everything is in units of the Earth. So the Earth is a little green dot at 1, 1. It's measured in Earth units as itself. You can see Venus and Mars fall on the dash curve, which shows a composition similar to that of the solar system terrestrial planets. And then the colored regions are the probability distributions of each of these planet measurements that we made with those 4 years of data. And as Vicky said, you can see these all lie a little bit above this dash curve. So that's what told us that these planets are slightly less dense than our solar system planets. If these planets had a solar system-like composition, we'd expect them to fall right along that dash curve, but they all are offset. And it's only with these very precise measurements that we could discern that offset. Previous data weren't good enough to do that.
Wow. So the precision is really a matter of taking the time.
Exactly, yeah.
That's fascinating because, obviously we live in a world now where we have computers that are able to, do, the kind of work that would have taken, humans alone so much time, but observation still takes just as long.
Yes, and in the past,
can't speed that up with gigabytes.
Exactly. In the past, people had to be a lot more patient with their solar system because the planets in the outer solar system take decades to orbit. So fortunately, with these short period planets are at Trappist-1, we can do it in a few years instead of having to wait lifetimes.
But although that does explain why all of the ancient philosophers and astronomers that we hear of had incredibly long beards. they were waiting a long time.
Exactly. But decided not to shave until they got the data.
Now, I love the chart that you had comparing the Trappist-1 exoplanets to our planets. But Vicky, can you tell us a little more in depth how our small town planets compare to those big city exoplanets?
Yeah, I mean, sort of a summary of what I've said before. The Trappist-1 planets are similar size but less dense overall. So you can kind of think of them as cousins to our planets. It's very likely they have, that they're terrestrial to some degree, but they're a different kind of terrestrial. They've either got much higher volatile content or a very different core mantle structure. And so I think that's super exciting. The one thing that is probably quite different about them that you can't really tell from just measuring them is that the kind of star they orbit, that TRAPPIST-1 is this teeny tiny little M-dwarf star that nonetheless might have been quite fierce when it was young. So M-dwarf stars tend to have a lot of activity and brightness when they're young until they finally settle down onto the main sequence, which is where stars end up and to spend most of their lives. And because of that, these planets have probably undergone a very different history, a very different life. They had a very different sort of experience than our planets have, because our sun didn't go through that wild early phase. And so that's also truly, truly fascinating about these. We don't know from the masses alone how that has changed things. So maybe it's giving us a hint in the different density. But I think the most exciting thing will be actually looking at these planets to figure out what their atmospheres are like, and then maybe trying to see if we can tell that these planets had a different history to our own.
Interesting. So for anybody who's just joining us or missed our intro, we are talking with Victoria Meadows and Eric Egel about the latest results about the 7 planets orbiting the nearby star TRAPPIST-1. So right now, let's see if we have a few questions to ask you astronomers.
Okay.
Here we go. This one is let's start personal. What got you guys interested in studying exoplanets? Vicky?
Well, I've always been interested in planets in general. So I did a really interesting PhD thesis where I observed a whole bunch of different things. But my favorite thing that I observed was the planet Venus, which is shown here in image 9. And so I got to know Venus pretty well. I actually searched for water vapor in its lower atmosphere, and I looked at oxygen air glow in its upper atmosphere. And I joke that, I became an astrobiologist, but I started off by studying water and oxygen on the least habitable planet in the solar system. And again, those things are there not because that planet is habitable, but just because of sort of the different phenomena that we were looking at, the greenhouse effect near the surface and also the air glow and the motions of the upper atmosphere. So that's what we were looking at. So I've always been very interested in terrestrial planets. I've never met a terrestrial planet I didn't like. And so I've always been interested in seeing, again, whether we can compare planets in our solar system to other planets out there. So so learning about exoplanets, whether they're like our own terrestrial planets and whether or not they're potentially habitable and able to support life is kind of the trajectory that I took in my career.
I see. Eric, how about you?
I got into it sort of by chance. So when I was first a graduate student, the first exoplanets were found around the pulsar, which is similar to black holes, which I was also interested in. But I felt with one planetary system orbiting this really exotic neutron star or pulsar, it didn't really make sense to pursue that as a career. And so I spent my PhD studying black holes, which was pretty fulfilling. I ended up working on an idea that led to the Event Horizon Telescope, which imaged a black hole, which was announced a year plus ago. But in the mid-90s, other exoplanets were found around more sun-like stars, and the numbers started to grow and became more interesting. And so by kind of a coincidence, when I was working on gravitational lensing to study black holes, I realized some of the equations applied back to exoplanet systems. And so that was my entry back in early 2000s into the exoplanet field. And I think most different than Vicky, I didn't have much background in planetary science. I was more interested in the thrill of the chase and the novelty of discovering something new. And in addition, it didn't hurt that exoplanets were somewhat more interesting than black holes because we actually live on a planet, so humans feel like they can maybe relate to planets a little better than black holes. Black holes are pretty fascinating as well.
Wow, that is fascinating. So you went from pulsars to black holes to exoplanets.
Yeah, exactly.
Interesting. All right, guys, let me ask you this. What do you see as the next steps in studying TRAPPIST-1? And please tell me the next steps don't include Elon Musk.
Maybe I'll leap into that one first. I think that, again, getting spectra of the atmospheres and having that potentially tell us about the history of these planets, whether they've lost atmospheres or lost oceans, being able to tell whether we see hints that they're habitable or not habitable, so whether they have an ocean or not, and also looking for life. And you might think, well, that's like a really grand goal that we can't do for like decades. But no, with the James Webb Space Telescope, which is scheduled for launch this year, hopefully, the end of it, I think that we are going to have the capability, potentially, to observe the atmospheres of these Trappist planets. And that is pretty exciting. So we're going to use the fact that they transit in front of their star to get observations of the atmosphere. And we do that by looking for wavelengths at which the planet appears to get bigger. So in some colors of light, it'll be one size, and in other colors, it'll appear to get bigger. And that's because the atmosphere around it is actually absorbing the light at those wavelengths. So it tells us there's something in the atmosphere that's absorbing. So that could be an oxygen molecule or a water molecule or a carbon dioxide molecule. And so it gives us, a chance to figure out what's going on in their atmospheres. So if we can do that, and even if we detect only a few different types of molecules, we can start to learn about the history of these planets, again, whether they've lost an ocean, and start to get at potentially maybe even just simple pairs of gases that don't seem to want to coexist with each other that might potentially indicate life. So that is potentially possible in the next 5 years or so, given, whenever JWST launches.
Okay. Wow. Okay. So James Webb is going to help us get more data on exoplanets. Eric, what do you see as the next steps other than what Vicki just said?
Yes, well, I am very excited about the James Webb Space Telescope as well. And in getting the spectra that Vicki mentioned, it will actually be very difficult to do that experiment. And so it's going to take many observations of many transits of each planet in front of the star to try to detect that very thin atmosphere that these potentially have. And so many transits means that we'll get many transit times. And so we'll actually be able to probe with much more precision the masses and orbits of these planets. So we're actually going to be able to even better characterize their bulk densities and pin down even better whether they continue to show this really common composition. They all seem to have a very small scatter about a single composition, which is fascinating, especially that it's offset from the solar system. And with that data, we can actually check to see that the assumptions in our analysis are correct. And so we'll be able to pin down their properties, bulk properties more precisely, and in addition, at the same time, be able to measure their atmospheres. So the James Webb Space Telescope, we've applied to use, I think we put in something like 10 proposals, and we'll see if the time allocation committee is favorable to us and gives us some time to study these planets.
That's great. So it'll be a whole bunch of new data coming in.
Exactly.
We have one more question from Michael Harasimowicz. Actually, thank you, Michael, because this is a question I had as well. How far away is the Trappist-1 star system from us?
It is 40.5 light years away. We use parsecs, so I had to pause for a second because it's a different the center of the galaxy is about 25,000 light years away. So we've been saying Trappist-1 is this close star. Well, it's a relative. So 40 light years is very close relative to the size of the galaxy as a whole. That's one of the great advantages of studying this particular planet system is the close proximity of the star, in addition to the fact the star is so small, which makes the planets easier to study relative to the small size of the star.
I see. Okay, so we didn't travel very far to get to that big city. So basically, we didn't come from Ohio. We came from, I don't know, Irvington.
Exactly.
That's okay. 40.5. It's funny because, as a sci-fi reader, I've rarely heard a light year measured in such a small number. Like you said, it's usually 25,000 light years, a million, 40.5. Like a half a light year? Oh, here's one more question. Are there any other Earth-sized planets that have masses like in Trappist-1? Not sure who this question is from, but I guess in studies of other galaxies, are there other Earth-sized planets that have masses? Who wants to take that? Is that an astrobiology question?
That's an Eric question for the mass.
Yeah,
that's an Eric.
But I can talk about other Earth-sized planets, but for masses, I'll ask Eric.
Yeah. Yeah. So for masses, Trappist-1 right now is the best we can do. There are some other similar Earth-sized planets that have mass measurements that are very low precision. We also have larger planets for which we have mass measurements that are fairly good precision, but still none really quite compare to Trappist-1. The best comparison actually is to our own solar system. And so in some ways, these measurements are kind of taking planetary science to another solar system, which is really exciting as far as the terrestrial planets are concerned.
And I will say there are other Earth-sized planets that we know out there, some of them very interesting because they're also in the habitable zones of their parent stars. But there are others that are interesting that are not in their habitable zones. They're much closer to the star than the habitable zone. We call these exovenuses. And so these are what appears to be terrestrial planets very close to their star that might have some similarity with Venus in our solar system. And so we're very interested also to get spectra of those with the James Webb Space Telescope. And potentially see if they have dense carbon dioxide atmospheres or no atmosphere or dense oxygen atmospheres, or, what happened to these guys? What was their history like? How did they turn out?
Mm-hmm.
And Vicky, that's interesting that they are Venus-like planets, because obviously that's your sweet spot.
Yep. Yeah. So even though I'm an astrobiologist and my first love is the habitable planets, I'm still very interested in how planets lose their habitability, and that evolution, what happens to those planets over time and how do they end up, because that's a big question for us as humans as well as, how do terrestrial planets, how do their atmospheres and surfaces and interiors evolve, and what are we going to end up like eventually? Right.
That's right. Yeah, that's true. Using data to look into the future. Now, here's a question from Marissa Myers. Do you see similarities between Trappist-1 and Gliese 180? Anybody feel like they have a handle on that?
Yeah, I can address that. So there's an interesting thing that, so the Kepler spacecraft found a lot of small planets similar in size to Earth, but around very distant stars. And those stars were too far away to use the Doppler technique to measure the masses of those planets. And so we have sizes, but no masses. So we couldn't compute the densities of those planets. There's other stellar systems like Gliese 180 that Marissa's asking about, where the planets have been detected with the Doppler technique, but the planets weren't edge on, so we couldn't see the transit. So we don't know the size of the planets because we don't know how big a shadow they cast across their star. And so the Trappist-1 system is kind of unique in that these planets are in their star's potential habitable zone if they have the right atmospheres for liquid water to host liquid water on the surface. But we also have both mass and radius measurements to compute the density, and so that makes it kind of unique. But otherwise, it is somewhat similar to the Gliese 180 system, although that has longer orbital period planets, and we don't have the sizes because they don't transit in front of their star.
I see. I just find it so fascinating that we're using shade and, shape to, get this amazingly precise science. I always say to my kids, like, no, human beings classify things according to shape and shade. And there's a reason, because you can get a whole lot of information just based on the shape and shade of something, especially over time. All right. Wow. Thank you guys for giving us so much fascinating information. Before we wrap up, do you guys have any, final thoughts, deep thoughts that you'd like to share with the audience? They don't have to be deep.
I think I'll go with that one. I think what I really want to get across to the audience is just how exciting this system is because of the small star, which means that we can, observe the atmospheres of these planets much more easily than any other system. And because of the James Webb Space Telescope, we are in the next 5 years going to start to learn about the atmospheres of planets like our own, but outside, orbiting around other stars, and we will have our very first chance to look for life. And I will say, extraterrestrial life. I will say that, that the chances that we'll see anything are probably low. We've only got 3 chances with those 3 planets, but still to start that search is really quite amazing.
Absolutely. Eric?
Well, so I mentioned at the beginning that the Trappist survey surveyed 50 stars. There's now, my Belgian colleagues are now doing a bigger survey called Speculoos, another backronym that spells the name of a Belgian cookie, that has bigger telescopes and more of them, and they're surveying 500 stars. So we're really excited about this Speculoos survey that it might find other Trappist-1-like systems. The other thing is that a lot of the science being done has a huge amount of data that's taken, and it's too much for astronomers to look through. So it's possible for the general public, for you to get involved in this search. You can go to the Zooniverse website, and there's several projects that involve exoplanets that you can actually look through data and potentially find something like we have done.
Really? A non-professional can go to, what was the site?
Zooniverse. It's like universe, but with zoo replacing the U.
Got it. So you can go there and have a non-professional can have access to some of this information and help sort through it?
Exactly, because the data amounts are so large, you can use a computer to distill down the data to some point, but you eventually have to look at it by eye, because it's really only a person's eye that can really see something that, is that a planet or not? And so it actually is very useful for astronomers to partner with the public in the search for exoplanets.
Excellent. And it's nice to hear you guys won't be replaced by robots anytime soon. All right. Thank you both for joining us here today. And thank you out there for watching and learning about the incredible Trappist-1 star system with us. Now, you can see this video as well as all of our other Universe Unplugged videos at the website, universeunplugged.org, or you can just click on the link in the comments that you should be able to see. So please subscribe on YouTube, and you'll be the first to know when our next Ask the Astronomers Live comes out. Follow us on Facebook to catch the live show. And until that next one, I'm Phil Lamar, here with Eric Agel and Vicki Meadows, and this has been Ask the Astronomers Live. Thanks for watching.
Thanks very much. I enjoyed it.